6.1 Entropy, a system property. Now we are going to look at the second law of thermodynamics from a quantitative perspective by introducing a new property called entropy. So entropy is a measure of the molecular disorder or a measure of irreversibilities of the system. It is an abstract concept. So energy is also an abstract concept. We are already familiar with energy. It is fairly easy to apply the energy conservation principles for a process. Entropy is not straightforward. Like mass and energy, entropy can be transferred across the system boundary, but entropy is not conserved. So entropy actually always increases for actual processes. So we'll get to learn how to set up the entropy balance equations. First, we will find out how to calculate the change in entropy. It starts from the Clausius inequality. So it states that for any cycle, the cyclic integral of delta Q divided by the temperature is always less than 0 for irreversible processes or equal to 0 for reversible processes. Consider a system at state 1 with specific volume V1. And the system goes through a process and ends at state 2. And the specific volume at state 2 is V2. So what is the change in specific volume during the process? It is simply the difference between the values at the final and the initial states. So delta V is V2 minus V1. From state 1 to state 2, there may be many different passes. But the change in specific volume is always the same for all processes. This is because the specific volume is a property. So it is not path dependent, but it is dependent on the state. A property is a point function. So it also applies to other properties such as pressure, temperature, internal energy, and enthalpy. So we don't need to know the path between the states to calculate the difference between the two states. Similarly, let's consider reversible cycles between the state 1 and state 2. So process A goes from state 1 to 2, and process B goes from state 2 to 1. So let's take a cyclic integral of delta Q over T between the two states. So it has two parts, integral from 1 to 2 and integral 2 to 1. The cyclic integral of delta Q over T equals 0. And this is because it consists of reversible processes. This is Clausius inequality. So integral from 1 to 2 equals negative integral 2 to 1. Integral from 1 to 2 through process A equals integral from 1 to 2 through process B. This concludes that the cyclic integral of delta Q over T is always the same for any internally reversible path between the two states 1 and 2. So it is independent of the path. It is a function of the end states only. Something must change between the two states. It has to be a property since it is only dependent on the end state. And this is what Clausius found. There exists a new thermodynamic variable at the states, and we call it entropy. denoted by S. So at state 1, entropy S1. At state 2, entropy S2. Entropy is a property. It is a property just like temperature, pressure, specific volumes, internal energy, and enthalpy. So delta Q over T depends on the end states only. It is a property. Let's say the differential property is ds. And that is equal to delta Q over temperature. So this is the definition of entropy. Or the change in entropy of a substance during a process is simply the difference between the entropy values at the final and initial state. So it is related to the heat transfer divided by the absolute temperature where the heat transfer occurs. So we must know the relation between the heat transfer and the temperature T to calculate the integration. So take a look at the equations. It is related to the heat transfer divided by the absolute temperature where the heat transfer occurs. We must know the relation between the heat transfer and temperature T to calculate the integration. Note that entropy change between the state 1 and 2 is same for all processes. It is independent of path. It is also independent whether the process is reversible or irreversible. Note that this relation is derived from internally reversible processes. But the result of it can be applied to any process, including reversible and irreversible processes. For example, the initial state is 1 and the final state is 2. It may undergo an irreversible process. But the entropy change between the two states is still the same, S2 minus S1. The capital S is the total entropy. So it is an extensive property. The lowercase s is the specific entropy. It is an intensive property. So what is the unit of entropy? So take a look at the equations. The unit of delta Q is kilojoule. And the unit of temperature is Kelvin. So unit of entropy is kilojoule per Kelvin. On a unit mass basis, so divide the equation by mass. Unit of specific entropy is kilojoule per kilogram Kelvin. And this is for specific entropy, and this is for total entropy. (6.2) Retrieving entropy data. We can look up the entropy values from the thermodynamic tables. Just like we did to determine the internal energy or enthalpy from the thermodynamics tables, we can determine entropy. So as the state principle describes, we need two intensive, independent properties to fix the state. So we can determine entropy from pressure and temperature. We can also determine entropy from pressure and specific volumes. Entropy can be also determined from temperature and specific volume. The entropy value is given relative to a datum, which is an arbitrary reference point. So let's take a look at the saturated water table. This is table A2. So in the thermodynamic table, the entropy of saturated liquid water at 0.01 degrees Celsius is set equal to 0. So this is an arbitrary datum. So there is no absolute value of entropy at a specific state. So instead, we are interested in the entropy change between the states. Let's work on a problem. Consider two states of water. At state 1, the pressure is 3 megapascal and the temperature is 500 degrees Celsius. We know two properties. They are intensive and independent. So we can fix the state. At state 2, pressure is 0.3 megapascal. The specific entropy is same as at state 1. So at state 2, pressure is given and the specific entropy is same as state 1. So we can fix the state. Determine the temperature at state 2. First, at state 1, pressure 3 megapascal. See table A4. Pressure 3 megapascal. Temperature 500 degrees Celsius. So entropy at this condition is 7.2338 kilojoule per kilogram Kelvin. At state 2, pressure is 0.3 megapascal and entropy S2 is same as the entropy at state 1, which is 7.2338 kilojoule per kilogram Kelvin. So we know two independent intensive property at state 2. So we can fix the state. So entropy 7.2338 sits between these two. So we can interpolate between these two temperatures. And T2 is calculated to be 183 degrees Celsius. If a substance is a saturated vapor and liquid mixture, we may use the quality to determine the property of the substance. So it is the same method we used to determine the internal energy and enthalpy using the quality. So the entropy is calculated using these equations. And we are going to work out this example. Determine the specific entropy of refrigerant 134A at a state where the temperature is 0 degrees Celsius and the specific internal energy is 138.43 kilojoule per kilogram. 0 degrees Celsius and the internal energy is in between these two numbers. So we know that it's saturated liquid vapor. So with a given internal energy value, we can determine the quality. So quality can be expressed for the internal energy. So internal energy for the saturated liquid. Internal energy for saturated vapor. So quality is determined. Now we use the quality to determine the entropy. Entropy for the saturated liquid is 0.1970. Entropy for saturated vapor 0.9190. So we can determine entropy. So we use the same method to determine the internal energy and enthalpy using a quality. The entropy of a compressed liquid for water may be found in thermodynamics tables. If the thermodynamics tables are not available, the substance may be approximated by the saturated liquid, and we use the saturated liquid vapor table. So let's see this example. Determine the specific entropy for water at 25 bar and 200 degrees Celsius. Let's say that compressed liquid data is not available for water at this condition. So we're going to use saturated water tables to approximate by the saturated liquid. So we know the pressure and temperature, 25 bar and 200 degrees Celsius. In table A2, this is the saturation temperature, saturation pressure. Table A3 shows saturation pressure and saturation temperature. So you may wonder which table should I use. In compressed liquid region, the property is a strong function of temperature, not pressure. So we should use table A2. So at 200 degrees Celsius, the compressed liquid may be approximated by the saturated liquid. So entropy for the saturated liquid is 2.3309 kJ per kilogram Kelvin. Do not determine the entropy based on the pressure. The thermodynamic properties are also shown in temperature entropy diagram or TS diagram and enthalpy entropy diagram or HS diagram. So HS diagram is also called a Mollier diagram. This is Mollier diagram. So these diagrams are useful as they visualize the change in thermodynamic property. So on TS diagram, we have a vapor dome, and this is saturated liquid line and saturated vapor line. And we have constant pressure and another constant pressure and constant enthalpy line. On Mollier diagram, y-axis enthalpy, x-axis entropy. This is saturated liquid line and this is saturated vapor line. So the critical point is here. On the other hand, on TS diagram, critical points at the top of the vapor dome. And this is constant pressure line. We have constant temperature line. So we are not using these tables to retrieve thermodynamic data, but it will be useful to visualize the state. Introducing TDS equations. We are going to calculate the entropy change. And the first law of thermodynamics, all energy balance equations can be expressed in differential form. Energy balance equation is Q minus W equals delta U, neglecting the kinetic energy change and potential energy change. And it can be expressed in differential form. Delta Q equals du plus delta W. And let's consider internally reversible process. It's a simple compressible system. From the definitions of entropy, delta Q over T equals ds. So we can write delta Q equals TdS. And delta W equals P times dV if it only involves boundary work. And this is very important equations. It is called the first TdS equations. It is also called Gibbs equations. TDS equation may be also expressed in terms of enthalpy. To relate the entropy to the enthalpy, we take the definitions of enthalpy. So enthalpy, H equals U, internal energy plus PV, flow work. So express it in differential form. dH equals du plus PdV plus VdP. And we write it for du plus PdV equals dH minus VdP. And du plus PdV is TDS. So TDS equals dH minus VdP. And this is called second TDS equations. So entropy change is expressed in terms of enthalpy. So there are two important TDS equations that can be used to determine the entropy change during a process. So entropy change is related to other properties that are easier to be determined. So entropy change here is expressed in terms of internal energy, pressure, and volume change. Entropy change is expressed in terms of enthalpy change, volume, and pressure change. So divide the equations by mass. We can also express the TDS equations in terms of intensive properties. So recall that entropy is a property. The change in property between the states is independent of path. So TDS equations may be also used for reversible processes because the change in entropy between the states is independent of path. Consider a change in phase from saturated liquid to saturated vapor at constant pressure. So TDS equations, TDS, dH minus VdP. At constant pressure, this term goes away. So ds equals dH over T. And integrate the equations between saturated liquid and saturated vapor. So Sg minus Sf equals Hg minus Hf, enthalpy change between the saturated liquid and saturated vapor, divided by temperature, and temperature is constant. So based on this, from the knowledge of enthalpy change between the two states, we can determine the entropy change between the two states. For example, determine the entropy change between the saturated liquid and saturated vapor using enthalpy change for refrigerant 134A at 0 degrees Celsius. So at 0 degrees Celsius, we can determine enthalpy change, which is 197.21 kilojoule per kilogram. And based on this, we can determine entropy change, enthalpy change over temperature, which is 197.21 temperature 0 degrees Celsius. Always remember, we use absolute temperature, which is 0.7220. So since we have entropy data for saturated liquid and saturated vapor, we can also directly calculate the values. 0.9190 minus 0.1970. So we get the same result. 6.4 Entropy change of an incompressible substance. So liquids and solids may be approximated as incompressible substances. So we can simplify the TdS equations for incompressible substances. The specific volume does not change significantly during a process, so dV terms go away. The internal energy for incompressible substances is a function of temperature alone. So from the definition of specific heat, CV equals du over dt, or du equals CV dt. For incompressible substances, the specific heat at constant pressure is equal to the specific heat at constant volume. So we denote the specific heat by C with no subscript. So we got ds equals du over t, and plug this in. So ds equals c dt over t. And the specific heat is typically a function of temperature. So take the integral from T1 to T2. T1 and T2 are temperatures at the initial and final states. So the change in entropy is expressed here. If we can assume the specific heat is constant, or take the average values over the temperature range, the entropy change is easily found. So if C is constant, take C out of the integrations. And the integral of 1 over T is natural log. So entropy change is C times natural log T2 over T1. And this is for incompressible substance with constant specific heat. Let's work on an example. Consider a system consisting of liquid water initially at 300 Kelvin 2 bar, undergoing a process to a final state 323 Kelvin 1 bar. Evaluate the change in specific entropy. So we have a liquid water, so we can assume it's an incompressible substance. Then we are going to assume it has a constant specific heat. C is 4.18 kilojoule per kilogram Kelvin, and this can be found at the back of the textbook. So the entropy change specific heat times natural log temperature T2 over T1, it should be absolute temperature. So the entropy change is 0.309. And this is for incompressible substance with constant specific heat.